Today we're going to be talking about how to find parametric and symmetric equations of a line. And in this particular problem, we've been given the line which passes through two coordinate points. One is 0, 1/2, 1, and the other is 2, 1, -3. Well, how are we going to find parametric and symmetric equations for this line passing through these 2 points? The easiest way to do it is with a vector representation of the line that passes through these points. How do we get a vector representation? Well, we've got these 2 points and we can represent them as vectors like this, 0, 1/2, 1, and 2, 1, -3. But what we really need are the direction numbers that define the direction of the line when the line moves from one point to the other point. And the way that we get those direction numbers is by subtracting the component parts of one of these points from the component parts of the other. So here's what that looks like. We will take the component parts of this second point, 2, 1, -3. So we'll start with here 2, the x component of this point, and we'll subtract the x component from this first point, which is 0, so -0. Then we'll take the y component and subtract the other one, so 1 minus 1/2, and we always want to go in the same direction, so we always want to start with the second point and subtract the component from the first point. And then we'll start with -3 and subtract 1, so -1 like this, and when we simplify, we get 2, 1/2, and -3 minus 1 is a -4. These are our direction numbers. This is a vector which is parallel to our line because we basically found a vector that goes from one point to the other point. These vectors that we defined earlier go from the origin out to this coordinate point and from the origin out to this coordinate point. So these 2 vectors move from the origin to the coordinate points. This vector moves from one coordinate point to the other, which means that it's parallel to the line that passes through these 2 points. And remember that because this vector represents the direction of the line, we also call these values here the direction numbers of our line. Now, in order to find parametric equations of the line, the first thing we want to do is write an equation for the line in vector form, or a vector equation of the line. And we're going to define that as r. We're going to say r is equal to, here's where we need to pick one of the points that our line passes through. And in this particular case, we'll pick 2, 1, -3, but it doesn't really matter. So we'll say 2, 1, -3. Remember that that's also the same as 2i plus 1j minus 3k. So we'll say 2i plus j, 1j, minus 3k, so it passes through that point. Then we add to that t, which is going to be a parameter value, times our direction numbers in vector form. So we're going to do the same thing, 2i plus 1/2 j minus 4k. This is going to give us the vector equation of our line. All we need to do now is simplify this by gathering together our components. We want all of our i's together, our j's together, and our k's together. So here's how we're going to do that. First, we're going to distribute the t. So we're going to get 2i plus j minus 3k. Then we're going to say plus 2ti plus 1/2 tj minus 4tk. Now we want to group our components together. So when we group our i's together, we get 2i plus 2ti. Grouping our j's together, we'll get plus j, we have this 1j here, plus 1/2 tj. And then grouping our k's together, we get plus -3k minus 4tk, like this. Now we want to factor out our components i, j, and k from these groups. So we want to pull an i out. When we pull i out, we're just left with 2 plus 2t, and we want to put the i behind this value so that 2 plus 2t is like a coefficient on this i component. Then here we want to pull out a j. We're left with 1 plus 1/2 t times j. And then we want to pull out a k, and of course we're just left with -3 minus 4t, and we pull the k out behind it like this. The reason this is so convenient, remember this is the vector equation of the line, but the reason this is so convenient is because we have everything we need now to find the parametric equations of the line. Remember that i, j, and k correspond to x, y, and z, respectively. All we need to do is pull the coefficients that are in front of these I, j, and k components here, pull these coefficients out and set them equal to the variables to which they correspond. So here's what that looks like. Our parametric equations, which we'll just say PEs there, we're going to say x is equal to this coefficient. So x equals 2 plus 2t. We'll say y equals 1 plus 1/2 t, and we'll say z is equal to -3 minus 4t. And that's it. Now we just need to find our symmetric equations of the line, which is going to be really easy because all we need to do that is 1 point on the line and our direction numbers. So here's what that looks like. We'll say symmetric equations, SEs. Let's again use the point 2, 1, -3, although it doesn't matter, you could use either of them. But here's what we're going to do. We're going to say x minus the x component from the point on the line, so x minus 2 in this case. And then we're going to divide by the associated direction number, which is 2, we can see here. So we're going to get x minus 2 divided by 2. We're going to set that equal to y minus our y value from our coordinate point, which is 1. And then we're going to divide by the associated direction number, which is 1/2. So divided by 1/2, set that equal to z minus the z value from our coordinate point, which is -3. And then we divide that by the associated direction number, which is going to be -4. Remember that with symmetric equations, you always set them equal to each other like this. In our numerator, you always say the variable minus the associated value from the coordinate point there. And now it's just a matter of simplifying. Keep in mind also that if we have a direction number that's 0, if any of our direction numbers are 0, then we pull that outside of our symmetric equation. So here's what we mean. If our direction numbers instead of 2, 1/2, -4 were 0, 1/2, -4, then our symmetric equations would look like this. Because we can't put that 0 for x here in our denominator, we'd have x minus 2 divided by 0, and we can't divide by 0. We just don't include it. We pull this x minus 2 outside, so our symmetric equations would be like this. X minus 2, and then just the y and z equations set equal to each other. So y minus 1 divided by 1/2 is equal to z minus a -3 divided by -4. So we'd say our symmetric equations are x minus 2, and then separately, y minus 1 divided by 1/2 is equal to z minus a -3 over -4. So we just pull it out like that, and you'll do that for every symmetric equation for which the associated direction number is equal to 0. But in this case, none of our direction numbers are equal to 0, so we can set all 3 of these equations equal to one another. Now we just want to simplify, and simplifying here is really easy. For example, z minus a -3. Instead, we're just going to say z plus 3 to get rid of that double negative. And then we don't like to have a fraction here in the denominator if we can avoid it. So we're just going to multiply this fraction by 2 over 2. If we multiply by 2 over 2, then the denominator becomes 1. 1/2 times 2 is just 1. That's going to go away, and we'll just be left with 2y minus 2. So then our final answer for symmetric equations, we get x minus 2 divided by 2 is equal to 2y minus 2 is equal to z plus 3 divided by -4. And that's how you find parametric and symmetric equations when you have a line passing through 2 coordinate points.